Hi guys. This video is just going to take you through the examples in the polynomial applications maximizing area and volume packet. This is the one with the track on the first page. So there's like 4 different types of examples that I'm going to take you through, and you can refer back to this video whenever you need help with these particular examples. But the idea is that you watch the videos, take notes on the examples, and then work some problems on your own. So watch as much of it as you need to, or don't watch any of it if you don't need to, if you feel like you can do it on your own. All right, so we have a track, and there's a little story that goes along with it. You can read it in number 1, but basically it's a track, and all we know about the track is that the inside perimeter is 1,500 meters, and then it's made up of a rectangle, and these are 2 semicircles on the outer sides. Okay, and then, like I said, we know that the inside perimeter is 1,500 meters. Inside perimeter basically means if you were to run all the way around the track, right? If you were to run all the way around the track like this, you would run 1,500 meters. Okay. And part A suggests that we label the dimensions of the rectangle x, x and y. And then it also reminds us that the circumference of a circle is pi times diameter. And it's asking us to write an equation for the perimeter of the track. So let's take a look. We know that the perimeter is 1,500 meters, right? So we need an equation that says basically 1,500 equals something, some algebraic expression. All right, and it looks like we have the track, the 2 straight edges of the track are the 2 portions, the 2 x sides of the rectangle, right? So it looks like we have 2 x's. And then we are running around 1 semicircle and another semicircle. So altogether, it's 1 big circle that we're running around just in 2 pieces, right? So this would be half of the circumference of a circle. This would be the other half of the circumference of a circle. So overall, we have the full circumference of a circle, but the question is, what's the diameter of the circle? Well, we could see that the diameter of our circle is right here, is all the way, is the width of the track, basically. So it's y. So our perimeter is going to be the 2 x's from the rectangle plus pi times y, y being the diameter, right? And I can label that for you guys. Right, so y is the diameter of the circle, of the circular portions of the track. All right, so here's the equation for the perimeter. All right, and that's part A. Part B asks us to write an equation for the area of the rectangular football field as a function of x. Okay, so it's basically the same problems we've been doing. So the area of the rectangular football field, just the rectangle now, we can see is x times y. Well, that's not a function of x. We are going to need some expression for y. We're going to need to substitute something in for y. Okay, so we're going to go back up here to our perimeter equation and solve for y. So I'll write that. Solve perimeter for y. So that looks like we'll have 1,500 minus 2x equals pi times y. Divide everything by pi, and we end up with 1,500 minus 2x all over pi. And then, as we know from our previous experience, we're going to take this guy, substitute it in here, so that we can have an area formula as a function of x, x times 1,500 minus 2x over pi. It's not pretty. It's not as pretty as some of the other ones that we've looked at because you are dealing with pi's with these circular regions, but it's completely fine to just leave this expression like this. And at this point, we want to maximize, right? Part C says use your calculator to graph the function within a reasonable domain. Sketch your graph below, including all important points, because the goal here is to maximize the area of the football field. So this function being the area of the football field, we're going to grab our calculator and graph it, and then we're going to sketch it. But let's think for a second about the reasonable domain. Okay, we've talked about this a lot, but a reasonable domain, like what are we going to look at our calculator? So if we look here and we think about the fact that this is going to be a parabola, right? It's going to be a parabola upside down because we're maximizing area, right? What are the x-intercepts of this parabola going to be? Okay, well, we hopefully know that one of them is going to be 0, right? Because this is just zero product property. This factor can equal 0 or this factor can equal 0. So x could possibly be 0. That's obviously not going to help us maximize our area. But the other x-intercept is going to be whenever this portion equals 0, right? Whenever this factor equals 0. Well, this factor is going to equal 0 when x equals 750. If you're not sure how I did that, I really just set 150 minus 2x over pi equal to 0 and solved. So a reasonable domain is going to be something that encompasses the 0 to 750. Now our area is going to go pretty high. If we think about a track, right, the area of a track, it's going to be tens of thousands of square meters. So we're going to, if not more, so we're going to make sure that we have a decent y value to look at as well. All right, so here is the graph of this parabola, and you can kind of see the scale that I used, but I went from -5 to 800, and then from a little bit below 0, although you can't see that. And I ended up having to go to 100,000, right? Because this is a very, think about a football field. The area is going to be huge. Okay, so the question is, where is the maximum? Well, we could just think about it, right? And think, well, if my x-intercepts are 0 and 750, and I know a parabola is symmetric, it's going to be right in between, right? The x value of that maximum is going to be right in between 0 and 750. So that's going to be at 375.5. I'm going to see a maximum. And you can see, you can see right here that maximum is occurring at 89,524.5 roughly. So the maximum area of this football field is going to occur when x is 375.5 and when y, the maximum area, is 89,524.5. So again, that maximum area was 89,524.5 square meters. And then the dimensions that maximize the area of the field, well, we already know that the x dimension was 375.5, right? We got that from our graph. And then to find the y dimension, well, we know that if we go way back here, area was just x times y, right? So area was just x times y. So if I have x and I have my area, I can just divide those two numbers to find the y value, or the y dimension. And it looks like the y dimension is about 238.4 meters. And that's really it for this type of problem. Okay, I didn't draw the sketch of the graph, but I think that you guys get the idea with what I'd want you to include, right? Intercepts, maximum, show the scale, and label the graph.